Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And again, the topic comes from one of my subscribers wanting to know more about satellite imagery and the different types of imagery and the different things that those different types can tell us about what's going on in the atmosphere. And it is pretty fascinating how this has evolved over time and the amount of things that we can now derive and understand that we weren't able to for a long time. Maybe we understood the principles, we just weren't able to actually use real data to display those differences. But now that's very, very possible. All right, so let me put myself down here in the corner and we'll start off with just a few elementary facts about satellite imagery to get us started. The first one is that there are 16 different wavelengths that are used to produce satellite imagery, different types of imagery, each one telling a unique story about the atmosphere. Now, when I talk about wavelengths, every object in the universe is emitting radiation, but it emits that radiation at different wavelengths, okay? And so by differentiating between different wavelengths, we can get information that tells us different things about the atmosphere. For instance, there are 3 basic types of satellite imagery: visible imagery, which is, if you were up in a spaceship with a camera and took a picture of the clouds, that's what it would look like. Once the sun goes down, you can't do much with that, obviously. And then you have water vapor imagery, which is able to tell you how much water vapor or how little water vapor there is in the mid-levels of the atmosphere. And then you have infrared imagery, which can help you to tell the difference in cloud heights, okay, whether or not the clouds are low or high or in between. Now, the satellite measures the amount of radiation reaching the satellite and converts that to a temperature, okay? So if you have an infrared image that has a lot of yellows and oranges and reds on it, that's telling you the temperature of those clouds is very cold. And you can set up any color scale you want. You can go from a dark gray to a bright white, or you can, for those colder cloud tops, you can have all sorts of pretty colors. Think of something psychedelic from back in the 60s and 70s, and you can do anything you want as long as it highlights the thing that you want it to highlight. Okay, so for visible satellite imagery, a wavelength of 0.64 microns is used. Now, a micron is a millionth of a meter, okay? And you have what we call this electromagnetic spectrum, which goes all the way from very short wavelengths to very long wavelengths. And the wavelength that the human eye is sensible to is right in this number or around this number here of 0.64 microns, okay? There can be all sorts of other radiation reaching us, but the human eye is not able to detect it, okay, because it's not at the proper wavelength for the human eye to decipher what is going on. Okay, wavelengths of 6.2, 6.9, and 7.3 microns are used for water vapor imagery. Those are wavelengths that water vapor is particularly effective at emitting radiation, and so that can tell us where there are dry areas in the mid-levels of the atmosphere and where there are moist areas in the mid-levels. And then finally, wavelengths of 10.3, 11.2, and 12.3 microns are used for the traditional infrared satellite imagery, which again can be used at any time of day or night. The visible imagery, when it gets dark, can't do anything with it, but this type of imagery and the water vapor imagery is available 24/7. Okay, so here is a little graph or a little chart, not chart, picture, I guess, showing you the different amounts of radiation that a satellite may receive and the things that it can tell us about that. Now here, if there are no clouds present, the skies are clear, the first thing that the satellite is going to get radiation from is the ground, because the atmosphere itself is not a good emitter of radiation at all. And so as a result, in this case, the satellite will be detecting the temperature of the ground, okay? And this can be really interesting when on a clear night, you can basically see, the ground or cold ground, and then if there are rivers in there and lakes that have a warmer temperature, warmer water temperature, that will show up as a darker color. And when there's snow on the ground, you can see individual rivers and streams that are, obviously in between the areas that are covered by snow. So all sorts of neat stuff you can do with this. Now, over here, you have maybe a low-level cloud, and so this cloud absorbs all the radiation coming up from the ground. So we don't see any of this, but we do see radiation coming from the top of this cloud, and that's what the satellite measures. And then over here, you have the same low-level cloud, but you also have a higher-level cirrus cloud above it. And so the only thing the satellite is going to be able to measure is the radiation coming from the top of this cloud. It will no longer be able to see this whatsoever, okay? So this can be a little misleading because these clouds up here are cold, and if you set up your color scale so that it's, you know, a bright orange or red, it could look like, oh, that's a big thunderstorm there. Well, not necessarily, okay? What it could be showing is just some innocent high thin cirrus clouds at about 25,000 feet up, and there's nothing going on underneath it at all. Of course, if you have a big thunderstorm, then that's going to be a continuous cloud all the way from the lower part of the atmosphere up to here, and in that case, there is something significant going on, and that color scale will point that out very, very clearly. Now, here are two satellite loops from earlier today, the visible on the upper left and the infrared on the lower right. And yes, it is true that if you look at this up in here, these clouds look more impressive than these ones down in here, but basically they're all different shades of white and gray, okay? But over on the infrared, this really stands out, where these clouds are very cold. These are big thunderstorms towering high up into the atmosphere. And then these clouds here barely even show up, okay? Which means that they're much warmer clouds. They're much closer to the ground, don't extend all that high up into the atmosphere, and aren't capable of producing any significant weather. So this is a very, very useful tool in differentiating between low-level clouds, which aren't going to do much in terms of precipitation, and clouds that extend all the way from the lower part of the atmosphere way up into the upper part of the troposphere, which is where all the weather occurs, and that would show up as these types of colors here. Now, oh, let's see, I want to go back here. Hold on. I want to show you a little simulator here. And this comes from what is called the John Dutton Institute of Learning up at Penn State. John was a professor, an active professor when I was at Penn State. He's now Professor Emeritus, but he has this thing called the John Dutton Institute, which is a very cool, free educational tool about different things relating to meteorology. So I wanted to show you one of the tools that he has on his site here. And basically, you can, again, set up your color scheme any way you want to, but let's say that we have a fairly low-level cloud here, and we set the color scheme up so that it's going to show up as a darker gray. But then I can adjust this cloud layer to move up into the upper part of the troposphere, and there, on this particular color scale, it shows up as a much brighter white. Or if you wanted to use a color scale where you had oranges and yellows and reds when it gets really cold, then that's the way it would show up. Okay, so again, the satellite is measuring the amount of radiation that it's receiving from different levels of the atmosphere, and if the temperature is decreasing with height, it's going to show different temperatures based on whatever is emitting the radiation that the satellite is receiving, and that's going to tell us a lot about either how high or low the clouds are, or what the ground temperature is, whatever the situation happens to be. Okay, let me get the PowerPoint back up here, and we will move on ahead to the next slide. Now, this is the last thing I'm going to show you. This is a water vapor image, and again, this can be used 24/7. And if there are no clouds present, it can tell you the difference between moist areas and dry areas. And this type of imagery, the color scale is set up so the oranges and the yellows are very, very dry air, and then the darker colors are moist air. And then, of course, if you have actual cloud cover, that's going to show up like this, okay? But supposing it's a severe weather potential set up in the plains where you have a dry line and no thunderstorms have developed yet, this is the type of imagery that would show you the boundary between the moist air and the dry air. But this is in the mid-levels of the atmosphere, and early on in my career, I used to think, oh, if that's really dry air there, nothing can happen. Well, that's not true. With thunderstorms, you can have a lot of low-level moisture, and it's very dry in the mid-levels, but you can still get big thunderstorms to develop right in the middle of that mid-level dry air. And so you have to be careful about the way you interpret this, but in general, it does tell you the difference between the moist areas and the dry areas, even if there are no clouds present. All right, there are the credits. That is bonus weather video number 2 for this week. I hope that made a little bit of sense to you. The next bonus weather video will be coming up on Friday, and the next daily weather update coming up tomorrow. So in the meantime, have a wonderful Wednesday evening, everybody, and we'll talk to you again tomorrow. See you later.